It's been less than 3 weeks, 20 days to be exact, since the University of Chicago sent shockwaves through the quantum computing world with a discovery that promised to cut the physical requirements for fault-tolerant machines by a factor of 10 to 20. 20 days. And now they're back, not with a footnote, not with a minor refinement, but with something physicists are calling a completely different kind of shortcut, one that doesn't just make quantum computers smaller, it makes them fundamentally more capable. Researchers have just demonstrated for the first time in history a way to perform any quantum calculation imaginable using particles that don't exist anywhere else in the universe. Read that again. Particles that exist nowhere else in nature, created on purpose inside a machine to solve a problem that has haunted this field for over 20 years. To understand why this second breakthrough matters just as much as the first, and arguably in ways that could prove even more consequential, you need to understand a problem that sits at the very heart of building a genuinely useful quantum computer. A problem that has nothing to do with how many qubits you can physically pack into a machine. Even if you solve the qubit counting problem, even if you find, as University of Chicago researchers did just weeks earlier, a way to protect quantum information using dramatically fewer physical components, you still face a second, entirely separate wall. Because protecting quantum information from errors is only half the battle. The other half is actually being able to do something useful with that protected information once you have it. And it turns out that the codes engineers use to keep quantum data safe are, by their very nature, extremely limited in what kinds of operations they can perform directly. What most people are not seeing is that this limitation has quietly forced the entire quantum computing industry into a workaround so expensive, so resource-hungry, that it has been eating up a massive share of every quantum computer's total capacity long before the computer ever gets to run the calculation you actually wanted it to run. This workaround has a name, and once you understand what it actually costs, you'll understand exactly why this new University of Chicago breakthrough is being treated as such a big deal inside the physics community. It's called magic state distillation. Think about what the name itself is telling you. Distillation implies a process of purification, of taking something rough and impure and refining it down into something usable. And that's exactly what's happening here, except the raw material being refined is quantum information itself, and the process is brutally expensive. To perform certain essential operations on protected, error-corrected quantum information, engineers first have to prepare something called a magic state, a carefully constructed quantum resource that unlocks operations the error-correcting code cannot perform on its own. But creating one clean, usable magic state requires taking many noisy, imperfect versions and running them through repeated rounds of purification, essentially sacrificing a large pool of qubits just to produce one trustworthy result. According to physicists in the field, magic state distillation and its close cousin, magic state cultivation, are consistently described as the single most expensive operations in standard quantum error correction codes. Not one of the most expensive. The most expensive. This is not chaos. This is strategy of a very specific, very costly kind, one that has quietly been consuming a staggering share of every fault-tolerant quantum computer's total resources for years, and almost nobody outside the field has ever heard its name. This is exactly the problem that a team of scientists spanning 4 of the most respected institutions in quantum physics set out to attack. And the University of Chicago sat right at the center of it. The paper, titled Universal Gates, From Braiding and Fusing Anyone's on Quantum Hardware, was published in the journal Nature on July 15, 2026, barely more than 2 weeks after the University of Chicago's earlier qubit reduction breakthrough had finished making headlines. The team behind it brought together researchers from the University of Chicago's Pritzker School of Molecular Engineering, Harvard University, Stony Brook University, and the quantum computing company Quantinuum. Leading the University of Chicago's contribution was Ruben Verisin, an assistant professor of molecular engineering at UChicago's Pritzker School, working alongside Harvard physicist Ashvin Vishwanath's research group, whose graduate students Anasuya Lyons and Chu-Fan Bowen-Lo helped lead the experimental work. Quantinuum's own scientific lead in Munich, Henrik Dreyer, rounded out the collaboration as a co-author. 4 institutions, one shared target, a 23-year-old theoretical proposal that nobody had ever managed to fully realize on real quantum hardware until now. To understand what these researchers actually built, you first have to set aside everything you think you know about how information gets stored inside a quantum computer, because the approach at the center of this breakthrough doesn't use qubits in the traditional sense at all. It uses something stranger, something that Ruben Verisin himself describes in almost poetic terms. We demonstrated a so-called universal gate set, Verisin explained, meaning that if you store information in these emergent versions of quarks and you move them around, you can do any quantum computation you might want to do. Emergent versions of quarks, Sit with that phrase for a moment because it's doing a lot of work. These particles, called non-abelian anyons, don't exist as standalone objects anywhere in nature. You cannot mine them, isolate them, or find them floating freely in the universe. Instead, researchers create them artificially by using quantum circuits to link together many ordinary qubits into one enormous, deeply entangled state that behaves collectively like a brand new kind of particle, one with its own internal physics, its own rules, existing only inside the carefully controlled environment of a quantum processor. Varison described the underlying codes this way. The way I think about these codes is they're creating little universes, alternative universes, but ones that reflect some of the properties of our own. Think about what that actually means. These researchers aren't just programming a computer. They are, in a very real sense, building tiny pocket universes with their own internal laws of physics, purpose-built to solve a problem that ordinary quantum hardware cannot solve on its own. Here's what makes non-abelian anyons genuinely useful, rather than just scientifically fascinating. Every one of these particles carries an internal state, and that internal state physically changes whenever you take two of them and move them around each other in a process physicists call braiding. And crucially, the order in which you braid them matters enormously. Swap particle A around particle B first, then B around A, and you get a mathematically different result than if you'd done it the other way around. This is precisely what the word non-abelian means in mathematics, a fancy way of saying that the order of operations changes the outcome, and it's exactly this property that gives these particles their computational power. Because their quantum information isn't stored in any single isolated location, but is instead spread out across the entangled state of many particles working together, abelian anyons are inherently protected from the small, localized disturbances, the stray photons, the tiny vibrations, the whispers of heat that constantly threaten to corrupt ordinary qubits. And here's the part that turns this from an interesting physics curiosity into a genuine computational tool. The act of braiding these particles around each other doesn't just move them from one place to another, it performs a calculation. The motion itself is the computation. This wasn't the University of Chicago's first attempt at harnessing this exotic physics. And understanding why the earlier attempt fell short makes this new success land with far more weight. Back in 2024, a team that included Varison used a quantinium trapped ion quantum computer to create a different type of non-abelian anyone, one built from a mathematical symmetry group called D4, essentially the complete set of rotations and mirror image reflections that leave a square looking exactly the same. This 2024 result marked the very first demonstration of this specific kind of exotic quantum order running on real hardware, a genuine milestone in its own right. But it came with a frustrating limitation. Braiding those particular D4-based anyons around each other, no matter how creatively you arranged the choreography, simply could not access every operation a truly general-purpose quantum computer would need. Varison was refreshingly candid about the shortfall. In that work, we didn't demonstrate that those emergent forces were enough to do quantum computation, he said. That particular universe we created was not powerful enough. Read that again. The team had successfully built one of these exotic pocket universes, and then discovered that the physics inside it simply didn't have enough computational reach to do the job. That's the honest, scientifically rigorous kind of setback that makes what came next so much more compelling. So the team went back to the mathematics, and this time they chose a different foundation entirely. Instead of the symmetries of a square, they built their new anyons on a mathematical symmetry group called S3, the complete set of rotations and mirror image flips that leave an equilateral triangle looking unchanged. This might sound like an arbitrary swap, one abstract shape for another, but the underlying mathematical structure of S3 turned out to have exactly the properties needed for universal computation, properties that D4 simply didn't possess. There was just one catch. Unlocking that universal computational power required combining braiding with an entirely separate technique called fusion, a process where two anyons are deliberately merged together, and the outcome of that merger is read out as a measurement, extracting genuine computational information from the act of combination itself. This idea of pairing braiding with fusion wasn't new. It had actually been proposed theoretically all the way back in 2003 by a physicist named Carlos Mochon, who at the time was a graduate student working under the legendary Caltech physicist John Preskill, one of the most respected names in the entire history of quantum error correction. Think about that timeline for a moment. 23 years. An idea sketched out on paper by a graduate student in 2003 sat waiting, unrealized, through 2 decades of quantum computing's most turbulent, most uncertain years, through the era when the entire field was routinely dismissed as science fiction, all the way until a team spanning 4 institutions in 2026 finally had the hardware, the theoretical tools, and the experimental precision to actually build it. Turning that 23-year-old theoretical sketch into a working demonstration was no small feat. and it required substantial additional theoretical and experimental development that Motion's original 2003 proposal never fully worked out. The team built their new S3-based anyons on Quantinuum's H2 trapped ion quantum processor, a machine that entangled 54 individual qubits to create the exotic collective particle, states the experiment demanded. Using pairs of these anyons, the researchers encoded what they call topological quotrits, a term worth pausing on because it represents a genuine expansion beyond how quantum information is normally described. An ordinary qubit, the basic unit you've probably heard about in every previous quantum computing story, holds two possible states, conventionally described as 0 and 1, along with every quantum combination in between. A quotrit, by contrast, holds three distinct levels of information instead of two, packing more computational density into every single unit of protected quantum information. By braiding and fusing these topological quotrits together in carefully choreographed combinations, the team successfully demonstrated three distinct types of operations, one entangling gate produced through braiding, and two separate types of measurement produced through fusion. And when you combine all three of these operations together, in principle, you can reach absolutely any quantum computation you might ever want to perform, including entire categories of operations that braiding alone, no matter how cleverly arranged, could never access on its own. Now here is where this breakthrough directly connects back to that expensive, resource-draining problem we started with, the one called magic state distillation. Quantinuum's Henrik Dreyer, one of the paper's co-authors, laid out the stakes with striking clarity. Non-abelian codes are a dark horse in the race to quantum error correction, Dreyer said. In this work, we show the first universal gate set in a non-abelian code, which demonstrates that fault-tolerant computations can in principle be done without resorting to magic state distillation or cultivation, which are the most expensive operations in standard quantum error correction codes. Read that sentence again, slowly, because it's the single most important claim in this entire story, without resorting to magic state distillation. Think about what that could mean for the future architecture of quantum computers. If the standard approach forces engineers to sacrifice a massive pool of physical qubits just to purify a handful of usable magic states before a computer can even begin performing certain essential operations, and this new anyone-based approach can sidestep that expensive purification process entirely, then the resource savings compound directly on top of everything the University of Chicago's earlier QLDPC breakthrough already promised. One shortcut reduces the number of physical qubits needed to protect information in the first place. This second shortcut reduces the resources needed to actually compute with that protected information once you have it. Two entirely different bottlenecks tackled by two entirely different teams of researchers, both rooted in the same university, both landing within weeks of each other. The team didn't stop at demonstrating universal gates. In a genuinely remarkable additional result, they showed that these non-abelian anyons could be used to prepare a magic state directly, through purely topological operations, essentially generating the very resource that traditionally requires an expensive qubit-devouring distillation process, but doing it through the natural physics of anyone braiding and fusion instead. This is the kind of result that, if it holds up and scales, could fundamentally restructure how engineers think about building a fault-tolerant quantum computer from the ground up. Instead of designing a machine around the assumption that you'll need to sacrifice large blocks of qubits purely for magic state purification, you could design a machine where the exotic physics of the underlying code produces what you need as a natural byproduct of how the system already operates. Think about the difference between a factory that has to run an entire separate purification plant just to get clean water for its production line versus a factory built on a site with a natural spring running straight through it. Both factories end up with clean water. Only one of them had to build, staff, and continuously operate an expensive purification facility to get there. Before this story runs any further ahead of itself, it's worth pausing on exactly what these researchers did not claim, because the honest, scientifically careful version of this breakthrough matters just as much as the exciting version. And serious physicists have earned real trust in this field precisely by being upfront about the limits of their own results. In the current paper, Verison and his colleagues did not carry out active, ongoing error correction. What they demonstrated instead were the individual computational building blocks, proving that each piece works exactly as the theory predicted, and specifically verifying that the magic state they managed to prepare matched what theoretical calculations said it should look like. Verison himself was completely direct about this boundary. So far, we've ignored the question of error correction, he said. Here, it's more like a proof of principle. This concession matters enormously because it draws a clean, honest line between what has actually been demonstrated on real hardware today, a working universal gate set built from exotic particles, and what remains genuinely unfinished work for the future, namely combining this approach with a kind of continuous, real-time error correction that a genuinely fault-tolerant quantum computer would need to run for hours, days, or even weeks at a stretch, without losing its delicate quantum information. 54 qubits, while a genuinely impressive engineering feat on Quantinuum's trapped ion hardware, is also still a relatively modest scale compared to what a truly useful, industry-transforming quantum computer would eventually require. But here's why that honest limitation doesn't diminish the excitement surrounding this result. It actually sharpens it, because Verisin has already mapped out exactly where this research goes next, and he's not waiting around to start. Combining this approach with error correction is the natural next step, he said, before revealing that he is already collaborating with other researchers at the University of Chicago's Pritzker School of Molecular. Our engineering to develop entirely new methods for stabilizing non-abelian quantum memories over time. Think about what that collaboration actually represents. This isn't a single research group publishing one paper and moving on to an unrelated project. This is a university doubling down immediately on a research direction. It has strong reason to believe is genuinely promising, pulling together additional internal expertise to solve the very next problem in the pipeline before the ink on the first paper has even fully dried. This is not chaos. This is a research institution treating a scientific breakthrough the way a chess grandmaster treats a strong opening move, not as an endpoint to celebrate, but as a foundation to immediately build the next several moves on top of. Zoom out for a moment and consider just how remarkable it is that this entire story, the second University of Chicago linked quantum shortcut, unfolded within roughly 3 weeks of the first one, making global headlines. 20 days, according to the timeline connecting these two announcements, separated a breakthrough about dramatically reducing the physical qubit overhead needed for fault-tolerant quantum computing. From a breakthrough about dramatically reducing the resource cost of the operations those protected qubits actually need to perform. Two completely different research problems. Two completely different physical mechanisms, one rooted in quantum low-density parity check codes running on reconfigurable neutral atom arrays, the other rooted in the exotic braiding and fusion physics of particles that exist nowhere in nature outside a laboratory. Consider, too, the role that Quantinuum keeps playing across this rapidly expanding landscape of quantum breakthroughs. Because it's not a coincidence, it's a pattern worth understanding. Quantinuum's H2 trapped ion processor is the exact hardware platform where this anyon-based universal gate set was demonstrated. That same company's Helios quantum processor was also the platform where, in an entirely separate story covered previously on this channel, NVIDIA's NVQ-Link architecture achieved what was described as the world's first real-time use of a scalable decoder for a difficult category of quantum error-correcting codes, hitting a reaction time of 67 microseconds against a 2 millisecond requirement, a result that exceeded expectations by 32 times over. Two completely unrelated breakthroughs, pursued by different research teams asking entirely different scientific questions. Both chose Quantinuum's trapped ion hardware as the platform sophisticated enough and reliable enough to actually put their theories to the test. When the same piece of hardware keeps showing up as the trusted test bed across multiple independently significant results within the same handful of months, that tells you something meaningful about where the genuine cutting edge of experimental quantum computing currently sits. And it tells you that trapped ion technology, once considered by some observers to be a slower, more niche approach compared to flashier superconducting or neutral atom competitors, is proving itself indispensable precisely when the most delicate, most demanding experiments need a platform they can actually trust. Think, too, about what this specific breakthrough could eventually mean far beyond the walls of a physics laboratory, because the implications of dramatically cheaper, more efficient universal quantum computation ripple outward into nearly every field this channel has touched on before. If magic state distillation truly can be reduced or even bypassed through the natural physics of braided and fused anyons, the resource savings don't just make quantum computers marginally more efficient, they fundamentally change what becomes computationally reachable within a given machine's physical footprint. Drug discovery simulations that would have required an impossibly large, impossibly expensive quantum computer under the old resource assumptions might become achievable on a meaningfully smaller, more affordable machine instead. Materials science calculations aimed at discovering room temperature superconductors are a holy grail of physics research for decades, could become tractable years earlier than current roadmaps suggest. And on the security side of this equation, the same efficiency gains that make useful quantum computation cheaper to achieve also uncomfortably apply to the encryption-breaking algorithms that security researchers have been warning about, meaning every genuine efficiency breakthrough in universal quantum computation, however scientifically exciting, also nudges forward the timeline on which today's encryption standards eventually become vulnerable, reinforcing exactly why security experts have been urging organizations to begin their transition to quantum-resistant cryptography now, rather than waiting for some clearly defined future deadline that keeps getting revised earlier with each passing announcement like this one. There's a genuinely beautiful, almost poetic dimension to this story that's worth sitting with before we close, because it captures something true about how real scientific progress actually happens. Messier and slower and more collaborative than the clean, triumphant headlines usually let on. This entire breakthrough traces back to an idea that sat quietly on paper for 23 years, sketched out by a graduate student in 2003, working under a mentor who would go on to become one of the most influential physicists in the entire history of quantum error correction. For over 2 decades, that idea waited, not because nobody believed it, but because the experimental tools needed to actually build it. Precise enough control over individual qubits, sophisticated enough entanglement techniques, hardware stable enough to survive the delicate choreography of braiding and fusing exotic particles simply didn't exist yet. And then, within the span of a single year, first in 2024 with an important but ultimately insufficient demonstration using D4 symmetry, and now in 2026 with a genuinely universal result built on S3 symmetry, the same University of Chicago researcher who experienced that earlier, partial success returned, tried a different mathematical foundation, and this time, the pocket universe he built turned out to be powerful enough. Varison didn't just build the alternative universe, he learned from the first one that didn't quite work, adjusted the underlying physics, and built a second one that did. So where does all of this actually leave us? Sitting here in the summer of 2026, watching the University of Chicago produce 2 genuinely significant quantum computing breakthroughs within the space of roughly 3 weeks. The honest answer, the one that respects both the genuine excitement of this moment and the real scientific caution these researchers themselves have insisted on, is that we are watching multiple independent bottlenecks in quantum computing's roadmap toward practical usefulness get attacked simultaneously from multiple angles by researchers who increasingly seem to believe the multi-decade timeline this field has lived under for years is no longer the safest assumption to make. The qubit overhead problem is shrinking. The magic state distillation problem may have just found its first credible alternative path. And the researchers behind both of these breakthroughs are already, without pausing to fully celebrate, working on what comes next. If you want to understand where this rapidly compounding momentum leads, what happens when qubit-efficient error correction and distillation-free universal computation eventually get combined into a single working machine. That is exactly the story we'll be tracking as it unfolds. So make sure you're subscribed before that moment arrives, because if the pace of the last 3 weeks is any indication, it may not take very long at all. Before you go, I want to know what you think this rapid-fire pattern of breakthroughs actually signals. Do you believe we're watching the genuine early stages of quantum computing's escape velocity moment? The point where progress finally starts compounding rather than crawling forward one slow step at a time? Or do you think the real test still lies years ahead in the harder, less glamorous work of combining all these individual pieces into a single machine that can run reliably for days without breaking down? Leave your answer in the comments below, and as always, I read every single one.